So hello, we're the UAM team for Dr. Hwang's MAE 155B class. My name is Abhinav Pradhan. With me is Jake Igana, Marius Rue, and Zach Steffish. I'll start off with a fact. In 2017, vehicle carbon dioxide emissions in the US reached 1.87 billion metric tons, which is a staggering number. A lot of these emissions are actually concentrated in heavily populated urban areas as well, which is the primary driver of our mission to design an urban air mobility or UAM aircraft. This aircraft would not only reduce congestion in heavily populated urban centers, but it would also offer a greener, environmentally friendly alternative to fuel burning vehicles. However, we're not the only organization with this mission. There's been a big push to design a viable electric transport aircraft for use in urban centers. And finally, we have an expected entry into service or EIS date of 2029. This is where BumbleBee enters the picture. As an eVTOL aircraft, BumbleBee will, one, be electric, making it sustainable, and two, have vertical takeoff and landing capabilities, making it maneuverable in tight corridors and environments. The vision for this project is to design an aircraft that can carry passengers to and from their destinations at rates comparable to UberX.
Now, just some comments concerning the main problem statement. Right now, we actually had two primary objective functions. And initially, we started with maximizing, or rather minimizing, our negative profit. And later on, we also added a secondary problem of minimizing negative range. Now, you can see there are a large number of design variables, but this can be summarized with three main categories. Namely, we have variables concerning aircraft shape and geometry. We have variables concerning motor performance. And lastly, we have a variable concerning battery weight. Now, these variables also comprise something called constraints, which are either other goals or other conditions that need to be satisfied in addition to maximizing or minimizing the objective functions. In our case, we have two kinds of constraints. Number one, we have stability constraints, which involve having no net forces and no net moments on a level flight aircraft. And in addition, we have a personal goal of having a minimum profit. So in other words, in this case, we want to have at least $75 million profit over 5 years. Just some relevant comments from our experience with GitHub, since this was our team's first experience with it. Initially, we did have significant challenge in ensuring that everyone could use version control effectively. And in particular, we found that there was a major source of failure for AppVeyor or app checker whenever a partial was computed slightly incorrectly. Because of this, we established a number of ground rules early on in order to make sure that each team member could use GitHub properly and efficiently.
So right now we're going to talk about the list of models. And to start off, we're going to have a look at the design structure matrix, or DSM. So the way this works is basically on the top row right here, you have all the design variables that Jake pointed out in the table. And so on the diagonal here, we have what's called groups. And so the design variables, they feed into the groups, and the output of the groups are other variables that are fed into other groups. And on this vertical connective line here, we have the constraints that Jake was talking about. And here, down here, this is the main objective function, profit, and for the first optimization problem, and range for the other. So this basically just represents the flow of our optimization problem. Moving on, now we're going to have a detailed look at the various physical models that we used. In terms of aerodynamics, we're using well-known formulas for lift and drag to calculate the lift coefficient and drag coefficient, CL and CD. However, we did make a few adjustments to account for the propeller wing interaction. And what this interaction is, so the propeller motion induces an axial velocity along the propeller disc. And so this axial velocity induces a blowing effect onto the wing, and where there's an additional movement of the air over the wing surface. And that affects the aerodynamic performance of the wing. And this adjustment was deemed appropriate because our design does have a total of 6 rotors, so there's significant propeller wing interaction. And in terms of drag, we did account for the various surfaces of the aircraft to include in our parasite drag formulation, and using drag buildup equation that account for the skin friction and drag of the fuselage, the wings, and the tail. And we also did consider the vortex lattice method as a more involved aerodynamic model, but we didn't think it was quite necessary for our goals, because our goals were more economics based. So we went with a lower fidelity aerodynamics model. In terms of propulsion, however, we did use a very high fidelity Glauert model. And this Glauert model is very good at accounting for the various losses in efficiency that are associated with propeller motion, which are eta1, the axial induced velocity, eta2, the rotational velocity, and eta3, the propeller blade drag, which is a skin friction. And the advantages are that you have more accurate modeling of the power consumption, and that is associated with the rotor operation. And power consumption is directly connected to energy consumption, which is basically the equivalent of fuel consumption for electric aviation. And the fuel consumption is obviously connected to the operating cost of the aircraft, and therefore is very relevant in our profit calculation. And on top, the Glauert model is already implemented in the OpenMDAO software that we're going to use, so it's readily accessible for us.
Concerning weights and stability, we opted for the weight equations found in Raymer's 2004 Design Aerospace textbook for multi-engine general aviation. And this is interesting because our aircraft is relatively new and novel. There aren't a lot of similar aircraft out there right now since it's still in development. However, we did feel that multi-engine general aviation was the best representation of our design.
So diving into the economics model, in order to calculate profit, we used equations modified from Dr. Hwang's paper on eVTOL economics. We developed a fare calculation per trip that takes into account a savings rate factor that puts a dollar amount to time saving of flying versus driving that equivalent distance. We wanted to calculate the profit over the first 5 years of operation. So we need to make some assumptions. Namely 250 aircraft flying about 2,000 flight hours per year per aircraft, which is a pretty standard value for general aviation for an aircraft of that size. We also assumed constant operating costs per kilometer, as well as energy costs consistent with that in the state of California. We also assumed, for simplicity, that ground and air miles are equivalent. And to calculate the acquisition cost of the aircraft, we used Raymer's development and procurement costs of aircraft, or DAPCA equations, but these needed to be modified to fit an electric aircraft. So instead of a fuel burning engine cost, we used modern day battery and motor costs instead. So just diving into the N2 diagram real quick. The N2 diagram is a useful way to visualize how the optimization software organizes and integrates the models that we chose to use. It also indicates how each input or design variable connects to its critical outputs. And as you can see, the propulsion group takes up a large proportion of our N2 diagram. And this is namely because there are 6 motors total, and each of those motors has 2 operating conditions, which are cruise and hover, meaning that each of those needs to be implemented individually. So you can see that each group connects to the next with the blue squares, indicating that the connections are working properly. So if there were red squares, that would indicate that something is disconnected and that needs to be fixed. But as you can see, everything is running smoothly.
So right now we're going to talk about the optimization results, and starting off with the first optimization problem that we solved, which was profit. So right now, so this is what's called a baseline optimization problem. And what this does is it keeps certain variables, in fact, the geometric variables of our optimization problem, it keeps those geometric design variables constant. So they're not involved in the actual optimization. And so the goal is to optimize the other variables around that, so to establish a baseline. And so what you can see here is the 5 design variables outside of the geometric design variables. So you got the area, the angle of attack for the wing, tail, the battery mass, and the airspeed, and this is our objective profit. And so we use an optimizer called Cobila. And so this, for the baseline, this actually didn't converge. So we set the iteration limits to 30,000, and the last value was $73.23 million. On the next slide right here, we can see the constraints that were introduced in the design optimization problem table. So these constraints for the baseline optimization, as you can see, they're not quite met. So what do I mean by this? So lift minus weight, or the which is during cruise, is about, if we skip to the end of the animation here, it's about 9.5. So that equilibrium is not met. However, it's fairly close because this is in newtons, and which is still a pretty small number. And the static margin is about 10%, which is acceptable because we set it the constraint between 6 and 20%. Some other of the constraints are met. The rolling moment and the pitching moment, they look pretty good, but overall for the baseline optimization, the constraints aren't really met. However, going to the actual optimization where we take into account all the design variables. So now if we run this animation right here, so you can clearly see all the design variables here are being optimized with the inclusion of the geometric design variables. And so actually now we achieve convergence with the Cobila optimizer after around 1,300 iterations, and the profit increased to $87.53 million. And also here you can see now with the actual design optimization that now the constraints are actually met. Excuse me, let me go back. The constraints are actually met, the equilibrium constraints, which is good. And you can see now the equilibrium conditions are satisfied. Now on to the second design optimization problem, which is range. It's the same procedure. So we start off with a baseline optimization. As you can see here, the iterations are set it to 10,000, and the range was 140 kilometers. And then with the constraints for the baseline optimization, they are better than for the profit, but they're still off. And so for the actual design optimization, for the range problem, you can see now they're actually converging after 1,225 iterations. And you can see the range improved to 163 kilometers, which is a great result after the baseline optimization. Similarly, the constraints, it's the same story. However, we did include the profit constraint for the range optimization problem. So the profit stays within $60 and $90 million at 87 million, which is a great number, in addition to the increased range. So this is just a quick summary of our optimization experience. So the profit increased by roughly 19.5%, from 73 million at the baseline to 87 million for the design. And the range increased from 140 kilometers to 163 kilometers after the baseline optimization, and that corresponds to an improvement of 16.4%. And just now, a quick word on the comparison of the optimizers, because we did try Cobila, as mentioned before, is a linear optimizer, and the usual practice is to use a nonlinear optimizers, which are SLSQP, Kahneman, and SNOP. However, for the profit design optimization problem, none of these really worked. Some of them converged like Kahneman and SNOP, but the results, they didn't satisfy the constraints, and they did not improve the objective function. And we do think that might be an issue with the way our Glauert model is set up in the code, but that would require further investigation. However, for the range problem, SNOP actually worked quite well. It actually converged, it did meet the constraints, and there was an improvement in the range output. However, it did not beat Cobila. Cobila still yielded better results, and SLSQP and Kahneman, unfortunately, were still not satisfactory.
So what's next for BumbleBee? With optimization, the possibilities are endless. So with the code that we have, we can now start looking into different optimization problems. A couple of examples are listed here. And we can also look into different higher fidelity models for aerodynamics, economics, weights and stabilities, and also take a look at different optimizers, not just the linear optimizers. Yeah, and here are references. Before we end the presentation, I'd like to say a few words of thanks to Dr. Hwang and Alex for providing an enlightening learning experience these last 2 quarters. We all agree that we've enjoyed this challenging yet rewarding class thoroughly. So thank you very much.
Thank you, Dr. Hwang. Definitely learned some great skills.
Thank you, Dr. Hwang.
Thank you.